In this video, I'm going to go over just basically the vocabulary we use when describing a wave. A lot of my examples, I'm going to draw out a transverse wave, but these would also apply to longitudinal waves, and I'll try to explain how a longitudinal wave might be different from a transverse wave. So the first term that you need to know is displacement, which is the distance the particle has moved from its rest position as the wave moves past. Okay, so if I was going to illustrate this on a transverse wave, so if I have a wave, and it looks something like this, and imagine this wave is being made by, we'll say, I have beads on a string, so there's lots of beads every once in a while on my string. So I would define there'd be a rest position that all the beads would have been on before I shook them, so that's this dotted line here, so that's our rest position. Okay, and how far they're displaced from the rest position is their displacement. So this bead right here has a displacement from the rest position of x, and as I go up to the top of my thing, I have a greater and greater displacement from particles, and then they start going down. The maximum displacement of my particles, so the farthest I'd be able to displace my particles from the rest position, so like this situation here and here, is what's called the amplitude. Okay, so my amplitude is maximum distance from the rest position. So if I wanted to show these same terms on a longitudinal wave instead of a transverse wave, the definitions are still the same, but it's going to look a little bit different. So on the top row of this diagram here is a bunch of, we'll say, ping pong balls attached to a spring, and we're going to push these ping pong balls together and make a longitudinal wave. So this top row represents the rest position of these ping pong balls, and I'm going to push them longitudinally so that I create a longitudinal wave in them, in this ping pong ball spring system, I guess. So you can see that as the wave travels through my ping pong balls, I displaced this ping pong ball number 2 from the rest position forward, and so it has a displacement, a positive displacement forward. If I looked at ping pong ball number 3, it's a little greater displacement than ping pong ball number 2, and ping pong ball number 4 has the maximum displacement from the rest position, and so that's my amplitude of my longitudinal wave. The next term you might need to know to understand what someone's talking about when they're describing a wave is crest. So a crest is just the peak or the high point of my wave, and another term you might hear is a trough, which is the low point of my wave. Another term you're going to need to know when describing your waves is wavelength, which we represent with the Greek letter lambda. Wavelength is the shortest distance between 2 points that are in the same phase of a wave. So we can measure this in a few ways. We can, on our longitudinal wave, we can measure it peak to peak or trough to trough. So if I measure this distance here, that would be one wavelength, let's write a lambda. Or if I just measured it from one point to the next point in the same phase, so at the start of one wave to the next start of a new wave, that would also be a wavelength. To find our wavelength on the longitudinal wave, it's a little bit harder, but we can use what we learned about compressions and rarefactions in the previous video to help find it. So on the longitudinal wave, I can find the wavelength as rarefaction to rarefaction or compression to compression. On the diagram below, the wavelength is shown from rarefaction to rarefaction. So if I measure rarefaction to rarefaction, I have one wavelength. Or if I measure compression to compression, because that's the point of a longitudinal wave that's in the same phase as the other point in the longitudinal wave. The next two terms which are important for you to understand and know are frequency and period. And these two terms are related, and they're very similar to what you learned about oscillations. So the frequency is the number of vibrations per second performed by the source of the wave. You could also think about it as the number of crests or troughs that pass through a fixed point per second. The unit that we're going to measure frequency in is going to be a hertz, which is equivalent to just something happening per second. Period is related to frequency in that it's the time that it takes to complete one complete oscillation of the particles. As we said before when we were talking about oscillations, frequency and period are very similar terms. So you can think of frequency as how often something happens, and you can think of period as how long it takes for something to happen. So frequency is the measure of how many oscillations per some time, and period is the measure of how long a single oscillation would take. This means they're related to each other inversely. So period is equal to 1 over frequency. The last thing we need to talk about is the wave's speed. When we talk about the speed of the wave, it's the speed at which the energy moves through the medium. And it's important to note that it's the speed that the energy is moving, not the speed at which the particles oscillate. So, for example, if I have my wave's energy in the top diagram here, my wave's moving in the direction of point A to point B, left to right. However, the particles, or the velocity of the rope which is oscillating up and down, because this is a longitudinal wave. So it's important to remember that it's the speed that the energy of the wave is moving, not the speed at which the particles are oscillating.